Hello, hello, hello. So this is a solo session, I'm sorry, and we are going to discuss a very beautiful thing, and it's very exciting. And so we'll begin. But before beginning, I want to tell you something. I want to show you something that comes in statistical mechanics, and I want to share my screen. So I hope my screen is visible. So I'll move, ensuring that it's getting recorded. Yeah. So I'll move and I'll show you something that's called the Maxwell-Boltzmann distribution. Okay, so let's see Maxwell. And there you go. You see a graph here. And in this graph, we have these distributions. So what you see here is the probability density and versus speed graph. So there are different speeds of the molecules. And what's the probability that, a particular speed will have the highest peak, highest value? And I mean, this is the kind of distribution, and what's the probability that, this particular speed has will be highest. It will be highest in the case of xenon. It won't be highest in the case of helium. In the case of helium, this particular speed somewhere here is going to be. So this, you see, what you see is a Gaussian, right? You see a Gaussian here, and you see something of the kind. I mean, like if I could zoom in here, you will find that this thing is actually an asymptote. It's asymptotic here, but it is not asymptotic here. It just ends there. You can't have a speed less than zero. Although you can have a velocity, but you can't really have a speed less than zero. So what this thing is telling us, I mean, if we obtain an equation, we do some kind of derivation. We do the derivation in the 101 statistical mechanics. We do the statistical counting, we minimize, and we come to a result. We use Lagrange multipliers, and then we use a Stirling, approximation, and so forth. We finally land up at something called the Maxwell-Boltzmann distribution function. Now, Maxwell-Boltzmann distribution function, it looks like this for speeds and different sort of stuff. But what this thing really means, I mean, how can this equation be doing this? So I have a very beautiful thing to discuss. So I'll just try to reload this, and I'll show you our wonderful stuff. So welcome to Desmos. It's a wonderful software, by the way. If you want to try it, it's a great thing if you haven't tried it already. So I'll simply play with some of these things, functions. So we say y equals, let's say it's x. So what you see on the screen is a straight line. Y is equal to x. So everywhere, I mean, here for example, here you have the value of x is, as you can see, it's 1.92, and the y is also 1.92, because, well, on this line, all the y's are equal to x. That's what it is. Anywhere you go, you see x and y. I can go on, I can use an exponential, let's say 2 to the power of, we get something of that kind. At this point, so this line, it crosses y-axis at certain point, it's always going to be 0, 1. Okay, always going to be 0, 1. I mean, you can check it if I use a different thing, if I use, let's say, y equals, let's say e to the power of x. Again, you see again here, it's always 0, 1. So exponential, it's always going to give you a 0, 1 on y-axis. That's the point where it crosses y-axis. So let's consider the second equation. Let's just remove this thing. We don't need it. How about I square this x in the exponential? How about if I put a negative sign there? Something of this kind. So that's pretty much Gaussian. Don't you see? Very, very special Gaussian. You don't have any unnecessary skewing or anything of that kind. It's If I put a variable right in front of E, I put it as a slider, just look what happens if I move this thing. So right now the value of M is 1. Right there, the value is 1. You see, it's 1. I slide this thing, if I increase, you see that? So let's fix it at 4. So M is equal to 4, and on this here it is also 4. I mean, you see what's really happening right there. I will not get into the details of how exponential is behaving away from the y-axis or in the vicinity of it, but we'll just see what happens if I put different variables here and there, and then I make a slider of it and then play around. So that's M. What if I put an X in between exponential and M? Doing it, and you see something of that kind. That's interesting. Well, if I can somehow, if I ignore this negative thing, this negative side of this thing, if I just consider this positive side, I see that this thing is actually skewed, you see? It's an asymptote here, and till infinity, it's an asymptote. It touches x-axis only at infinity. But right there, it's actually 0. So there is a skewness. It looks like a Gaussian, but it's not really a Gaussian. It's a skewed Gaussian. How about if I slide it? You see what's happened? You see what happens? Awesome, right? Okay. Now, what about if I put, something in the denominator? So something of that kind. If I put an n right there and I make a slider of it, observe what happens. Same thing, isn't it? Definitely. But this time, when I'm increasing it, you see it's fading away. In the case of M, if I increase it, exactly the opposite will happen. Let's observe. You see? Of course, it's obvious because it's in the denominator and M is in the numerator. It's the numerator. How about if I, introduce something else? Let's say that I introduce another a denominator here. So let's say in the or maybe something of that kind. Let's introduce a R there. Use it as slider. So what happens? That's nice. But notice it's not the way it was happening the last time. Last time this is what was happening. You see? And this time this is what's happening. You see? So what you must notice here is that when I'm sliding n or when I'm sliding m, when I'm sliding this coefficient thing in this equation, the slope of this part of the curve is actually changing. If we consider it to be a straight line, a line segment, and when we change n, look, observe how the slope will change. You see? But when I'm doing when I'm changing r, slope remains the same, and this kind of expansion happens. You see? Okay, so how about if I introduce another thing? I remove this stuff, and I say, well, let's add something right there. Let's say I am adding a s there. Okay. So let's make a slider of it, and let's see what happens. Oh my! Do you see? It's completely skewed. Something that we just saw. Can you see that? I mean, not really what we just saw, but it is kind of pretty much close to what we just saw. And if you see, it's asymptotic in this region. I mean, till infinity, it's asymptotic. But right there, it's converging to 0, and it has a 0 value right there, and skewed, heavily skewed. But for some reason, this thing looks pretty much, symmetric, although it's skewed, but it just looks, it appears, it's a delusion maybe. It appears pretty much symmetric, not so skewed, not heavily skewed as what we saw. But this thing, if you look at this one, this graph, it's pretty much skewed, isn't it? Okay, so I'll do another change here. So I'll introduce a bracket, and I'll put a square there. Yeah, and maybe okay. So all right. So just, isn't it beautiful? And it's not just the beauty that you must appreciate, but also, using this equation, we are able to form these kinds of, figures, these shapes, and we can change them by changing these variables. And the fact that these can be used, these changing figures, changing because of change in the variable in the equation, which you see on the left-hand side of the screen, using these this particular equation and just changing these variables, we can change the way this figure appears, and we can make it skewed, we can make it symmetrical, we can transform it into any form. And most importantly, it can actually be used to describe a process or maybe the state of something. So if I say that, well, if I just consider this thing, look at this, it's very much symmetrical, and we can use it to describe something of the kind. Just look at how, if I increase, what you see is this area, this thing is it's actually it's decreasing the area here, and there's an increase there, right? So just observe, it's describing a leaking process, isn't it? Something is getting leaked. How about quantum tunneling? Kind of that kind, if not exactly that. Definitely not that. But yeah, there's a kind of a leaking happening there, isn't it? Yeah, a very peculiar leak. If I change this thing, look at that. And if I change this thing, oops, okay. Look at that. And how about that one? M. It's a coefficient. It's a coefficient is simply, I can actually remove the underneath this M thing. So, is it gone? Why is it gone? And how about S? So, well, you see, when we're changing this S thing, you can actually move this figure here and there. You can move, you can displace the whole bell. When you do changes in M, you can you can like stretch it up, or maybe squeeze it down, and so forth. S changes this, M changes that. If I put an N there, now observe what happens. Look at that. So what you're really observing is something called standard deviation. So this is standard deviation. So N is something we use as standard deviation. It's called the standard deviation, and this thing S is the mean. All right. So the mean, it's actually, look at, so this is the highest point, right? Now observe how this highest point is actually changing when I change the value of S. So this is actually changing. Look at that point. So by changing this S in this sort of equation, you can change how the graph appears. I mean, where the mean is, highest point is. And by changing the value of n, which is here as well as there up in the exponential, in this particular form, you can change the, the broadness. You can make it narrow. You can make it broad. If you have this thing in mind, I mean, I would appreciate, I would advise that you go for Desmos and play around Desmos and try to understand what is this thing called the Gaussian distribution and how you can make it good. You can play with it, and using the intuition that you get from this kind of playing, you can try to interpret what these Maxwell distributions are actually. How can an equation describe these gaseous behaviors, different kinds of molecules in different setup, different conditions behaving in different ways. And if you change the mass, you get a different thing. I mean, what you see here, helium, neon, argon, xenon, they're simply molecules, atoms, basically, because they're inert. They're inert. So they're simply masses. You're changing the mass, and by changing the mass, you're actually able to change the peak, and you can change the value of the broadness or the narrowness. So for very high mass, you see that there is this thing is very narrow, and also it's high. It's really high, isn't it? And also the mean is very much close to zero. How about the least mass, helium? Well, you see it's very broad. It's not narrow as it was in the case of xenon. It's very broad. Secondly, it's very close. It's not as close to zero as xenon's graph. And you see that so I talked about narrowness, I talked about the mean, and the third thing is that this is not so high. This thing is very high. This is not so high. So by changing the mass of gas, by taking different gases, I get different curves, different behaviors. And what you see here is this M actually, increases the height of this curve. The N, which is the standard, we call it standard deviation, it makes it narrow, or makes it really broad. And so this was Z on. I mean, if you want. And thirdly, let me just finish it. And thirdly, this thing which is called the mean, it moves it. You see that? So if I were to produce this xenon thing, the xenon's graph, what would I do? Well, I want it to be very close to zero, so I make it very close to zero. There you go. It's pretty much close to zero. And it was very narrow, that of xenon. It was very narrow, so I can make it more narrower by changing not S, of course, not M, but N, because that's standard deviation. I can make it narrow. Look at that, how narrow it is. Okay. And thirdly, so it's very close to zero. It is narrow and it's high, right? How about if I copy this equation and I make another one? And maybe this time I'll change the color. So this is the other thing. Now, if I, okay, allowing me to change it. I think you did get the intuition. So if I wanted for, helium blue thing, increase uh, broadness, which was done by this. So this is broad now. I have to shift it away from 0. So, well, there you go. Let's make it more broader. Okay. And of course it's very low, it's not so high. So this is for, so look at how the same equation, I just modify a few, variables in this equation, and I'm able to, get intuition, a mathematical intuition for the behavior of different gases. It's an extraordinary feat, isn't it?